Now that we can switch patterns and compress our song data, we want to set up the actual sound processing. At first, let us specify the audio driver. Now we reserve the space key for play. We use the state of bit mask variable's 5th bits whether we stay in the edit mode or switch to the play mode. If the 5th bit is set, the play mode is enabled while the edit mode stays disabled. Don't mind the green text, I've made a mistake. We're handling the 5th bit, of course. We're counting bit 0 as well. Let's further create a process input for the play mode. After all, we want the ability to stop our music as well. Same mistake again. We're going to create code blocks for both the edit mode as well as the play mode. Second one will be the play mode. For testing purposes, I remove the draw everything function in the play mode to show you that the space key actually works. If you press play, we should see nothing but a blue screen. Now we want to draw the large play bar. If bitmask's 5th bit is set, the play bar is being drawn to the screen. It further contains variables such as the cursor play counter that moves the coordinates of the play bar every row cycle. The next step is writing functions that set our play bar to the 0th position after we played an entire pattern or cut the pattern before we reach the end, depending on our song settings. Let's compile and see if everything works properly. As you can see, the play bar rushes through the entire song. It's time to create the audio decoder. Now that we can go through every row of every pattern, we want to decode the data stored in the audio commands pointer and put that decoded data into a 28-byte large memory block that I name auxiliary array. At the end of this video sequence, we will show via print instruction whether we successfully extracted all commands from our encoded large data stream or not. When we start to play music, our decoder will process row by row the information that we will overhand later to our signal generators. Every row cycle we set the auxiliary array to default value 45 before it gets overwritten with actual sound command information. Before we are able to fill up the auxiliary array, we have to search the entry point in our data stream. Since our command values in our data stream are transformed by the number 17 if they're stored left of the separator number 126, we have to transform them back to their ASCII values. Let's add an print instruction and see what happens. Number 45 is the SQ value of this dash symbol that represents an empty cell. Let's see if the algorithm recognizes the values that we write into few of these cells. If you watch closely, you can see among all these 45 values are the SQ values we have put via fill cells function and the decoder into the audio commands pointer, and now back from the audio commands pointer decoded into the auxiliary array. Now we can overhand these commands to our sound generators that we will code next. Finally, we're going to set up our first signal generator. For every channel we have variables stored in data fields like frequency former row or volume former row or duty cycle former row. We want our generator to recognize a default frequency even if there is an empty row. Let's say we have set a note like C. What note does the synth play after 10 empty rows? Of course the frequency of the last setting we have made. The SDL-Q audio instruction queues our buffer memory block to the DA converter. This cycle repeats again and again until the bytes we have queued exceed 30,000 bytes. After 30,000 bytes, our program will sleep in a while loop until the next bytes remaining update tells the loop to stop because the size of bytes that are still queued to the DA converter falls below 30,000 bytes. This way we synchronize our graphical display to the actual sound in the background. The buffer also gets emptied after every cycle. If we just overwrite the stuff that is inside there, we would get messy signals. Now let's create the pulse generator. The values from C0 to C6 are the actual command values from each column of a certain channel. We get these command values, as you might guessed, from the auxiliary array pointer. The frequencies array contains floating point values of each keynote on a keyboard. A4 for example has the value of 440 Hz, which is a manifold of 27.5. Now we're going to build a manifold of one of the frequencies in the frequencies array, depending on which octave we've set. C4, respectively the fifth column, makes a request if we have set a vibrato or not. We're going to check the volume now. All these numbers are hex numbers, by the way. If our volume is set to 0, there is no sound at all, so we can jump to the end of the signal generator that saves us the process of filling our buffer. This is a more than 10,000 instructions large process, I guess, and frees a tremendous amount of computational resources. Let's check if commands for duty cycle are set. If not for the entirety of a pattern, we're falling back to the default duty cycle of 0.5. We're preparing all variables for our signal generator, like pulse width, when one single period is accomplished, when to start a new one, etc. Please watch video number 9 if you want to understand what's going on now. The sample clock determines our entry point into the pulse generator. We need to know where the position of our signal was the last row cycle when we filled up the buffer. That's it. That's the whole process. Now let's compile and see what we have accomplished now. Tiny corrections to make, but now. We're done with the first pulse channel, let's add the second one. That's not difficult in particular since we already set the foundations for everything. Let me show you what it would sound like if we haven't made the decision to add the sample clock that saves the entry point for the next row cycle. Kinda chopped signal because it doesn't fit into the buffer frame.